Welcome to qnawire.
Okay, so why is NH3 trigonal, tetrahedral instead of trigonal pyramidal? Well, what would be the hybridization? Well, first of all, what is the hybridization of NH3 as we know it, the tetrahedral form? This is sp3, right? Tetrahedral corresponds to sp3. That is, we've combined an s orbital and 3 p orbitals, right, to make 4 sp3 orbitals, right? And these arrange themselves in a tetrahedral fashion. Okay, and this is what we're doing with nitrogen, right? Nitrogen is in the middle, hydrogen the end of each. Okay. Well, what's going on if NH3 is trigonal planar, right? It obviously can't be sp3. sp3 hybridized nitrogen is tetrahedral. Trigonal planar would correspond to NH3 being sp2, right? The combination of an s orbital with 2 p orbitals and 1 p orbital just left out, right? Let me swap these real quick. Up and down one. Let's say it's really matter, but just to make it easier to. Okay, and then an unhybridized p orbital. Okay, right. So we get 3 sp3 orbitals, a little more p-like, and then 1 unhybridized p orbital. Okay, so nitrogen in the plane, 3 bonds to hydrogen, and then an unhybridized p orbital pointing straight up out at us. And from the side, it would look something like this. Okay. So why is there an energy difference here? Well, remember that when we bring orbitals together, we create bonding and antibonding orbitals, right? So if we bring an S, which has its own bonding and antibonding, and a couple of P's, which each have their own bonding and antibonding, right? What we end up with is a series of, these don't have their own bonding and antibonding. What am I doing? Right. When we bring them together, what we end up doing is generating a system like this, right? We get our s orbital combining with our p orbitals. The level they would be at. But instead, we're going to get 3 sp2 bonding orbitals and 3 sp2 antibonding orbitals. Okay. And then our p orbital, our unhybridized p orbital, will just have the same energy it always had, right? If we combine all 4 of them, right, then we're going to get essentially 4 bonding orbitals and 4 antibonding orbitals. Okay. And so if we were to fill these with electrons, we'd have 2, 3. See, we've got a lone pair, 2, 3, 4, 5. 2, 3, 4. Oh, and then the 3 from the hydrogen, so 8 electrons. We need to fill 8 electrons in here. Okay. That's if we don't hybridize. And if we do hybridize, right? So we get this energy benefit. The difference is between a lone pair being in an unhybridized p orbital, which would be here, or getting the energy benefit of moving it into a hybrid sp3 orbital, sp3 bonding orbital, right? So it's the difference between having a lone pair in an unhybridized p orbital and having an a pair of electrons in one of these lower energy hybridized sp3. sp3, lower energy, sp2, unhybridized p has a higher energy. Okay. And then the final thing has to do with the dipole moment. Okay, so let's say we've got our nitrogen. So that's lone pair. And then we've got hydrogen, hydrogen, and hydrogen. Okay, so our dipole moments and trigonal planar, and tetrahedral point up at nitrogen. Okay, and then they also point up at this lone pair. Okay, so if we viewed this from the top down, the parts that point in at nitrogen and not just up are all going to cancel out, right? So the net dipole is just going to be straight up, like that. Okay, so that's got a net dipole, a molecular dipole. That's why it's going to be polar. If instead we consider the planar case, where from the side, or where from the top we have nitrogen, and these hydrogens are all in a plane with each other, the bond dipoles will all point in at nitrogen, but they're all going to cancel out, right? So the amount that this one points in this direction is equal and opposite to the amount that this one points in the opposite direction, and this one points in the opposite direction. There's no net dipole. The 3 of these are all going to cancel each other out, and so this is going to be non-polar.